Thank you very much, Mark, for the introduction. It's a pleasure to have all of you in our audience. Thomas and me would like to talk with you in the next 30 minutes about humans and algorithms, about how we can create economic value from forecasting. To shine a little light upon this topic, I'd like to start with an example. Actually, the beginning of the week was rather nice, and I think some of you may have had a nice barbecue. But till you have those chicken legs on your grill, it takes quite some time. That's the beginning. The egg is hatching, you get a chicken. Chicken needs to be slaughtered, cleaned, processed, packed, made ready for transportation, and finally transported to the retail store where you can buy it. And then finally, you get this outside crispy, inside juicy Swiss bio chicken on your grill. Well, that's all fine if the weather was like in the beginning of the week. But if it looks more like Swiss weather, you probably don't want to have your barbecue, do you? So, no barbecue means all the processes here are in vain, and the initial product may have made better use in this form processed into, for example, pasta. Now if we compare these two products, pasta and chicken legs, which product do you think is more sensitive in its economic value to bad forecasting? So who thinks that pasta, the economic value of pasta, is more sensitive to bad forecasting? Who thinks that chicken legs, there the economic value is more sensitive to bad forecasting? Okay, that's the majority for the chicken legs. Well, we can again shine a little light upon this question by looking at some supply chain properties of these products. So the pasta definitely has a long shelf life, unless you buy fresh in Italy. But normally pasta long shelf life, typically also low costs, so it's not such an expensive product, and margins that are roughly around 12 to 20% for the retail. If you're looking at chicken legs, they have a shorter shelf life, they are more expensive in production, and they also have higher margins. So I would actually agree here, probably the chicken leg is more, that the economic value there is more sensitive to bad forecasting. Now forecasting, especially bad forecasting, is generally quite a pricey thing. We've done some research and calculated that 56 billion Swiss francs per year are wasted, literally, on the level of the retailers there. The consumer is not even included, so it's just industrial production, and retailers are wasting this amount of money in Northwest and South Europe. A little bit more difficult to argue, stock out. Again, a similar amount, one can argue, of course there are effects like substitution taking in, so it's a bit more hard to argue for this number, but still, it's in the same scale. Having seen this large potential that actually bad forecasting is causing, we founded the company PrognosiX in 2014, and in PrognosiX we are focusing on the co-development and on the marketing of forecasting algorithms. We especially want to incorporate human expertise into the forecasting process. Now, those of you who have just followed the interesting talk of Mr. Krohn, he actually said that nowadays still a lot of people influence the forecasts, and that's also our experience, so we really want to give them tools such they can do that smartly. This company, PrognosiX, is a spin-off of the Institute for Applied Simulation at ZHAW.
And that's probably where I come into the play as a representative of the Institute of Applied Simulation. Just let me quickly introduce the institute. We are the smallest institute of the Department of Life Science and Facility Management. We are roughly 40 people divided into 6 research groups, as you can see here. Which one is the pointer? our main topic actually is computational science, or more precisely computational life sciences. And please allow me to add a little advertisement here, because we have just launched a new program, Master Specialization in Applied Computational Life Sciences, which is kind of a data science and a simulation modeling program for people with a life science background or background in a life science discipline. So if you're interested, or probably you're not a target, but if you know people who are interested in this kind of program, please come to one of our info evenings or visit our website. Anyway, let me go on. Another reason why I'm here is because on ZHAW side, I'm also project leader of a CTI project together with PrognosiX, in which we basically developed the basic technology for PrognosiX. We also have other partners on board from the Migros Group, so Migros Zurich, Bischofsnahrungsmittel, Denner, and we have a software partner from Germany, Inform. And the results we are going to present now are kind of a side product of this CTI project.
Now, what challenges are we actually facing when doing forecasting in the food market? This is a typical sales series from one of our partners. Black is the sales, and you see very important facts about this time series. First of all, what you will see is there are some peaks in there. These peaks are usually explicable. They're usually due to external events like good, bad weather, or to internal strategies like promotions, price strategy, and so on. So that's one fact. Another fact is the time span you have. So here for this partner we do forecasts on a weekly basis. He's not interested what he's going to sell tomorrow. He wants to know what he needs for a full week. That's a little back in the supply chain. It's not on the retail store. So you have one data point per week, and that over a span of maybe 2.5 years, and that's luxurious. Because in the food market, it's a very dynamic market. So marketing strategies change, articles change. So if you have 2.5 years of data, that's quite luxurious. You see, obviously, such a series cannot be forecasted reasonably by classical algorithms like time series algorithms, even though they are still used nowadays. And there's also a problem if you want to apply smarter algorithms, because you have too little data. And you see here very nicely how this regression tree algorithm actually catches up with the peaks and manages to even predict their height, because it learns that some external drivers are related to those peaks. But the initial learning it takes for like probably 1 year until it manages to at least say where the peaks occur. It's way too long. So here we need human intelligence as well, because we cannot afford such a 1-year learning. Now, forecasting as it was done, or is still done nowadays in the food business, is like you have your forecasting technology, which consists of a small basis of algorithms, usually time series algorithms, standards. You have some evo metrics that help you to pick the best algorithm, and then you have a lot of human overrides. Because those humans, they know, okay, we have a promotion, so we have to override, or they know, okay, now I have a large stock, so I don't need that much items to order. What we are doing in this CTI project is we include directly these external drivers into the forecasting, and we also include the human expertise into this mechanism. We are using, of course, not just algorithms from the 1960s, but also algorithms from the 1980s, and a bit newer ones as well. And of course, we still have human overrides, because I think no algorithm can ever be as good as a human in the case of our data. We have just too little data for the real learning algorithms. And what we would like to focus on now in this talk is, well, whatever algorithms you're using, you'll have a problem of having to judge which are the best. Now you can do that either with evo metrics that are standard, which is however not what our industry partners want. They somehow want to include their economic considerations like their stock, their shelf life of their products, storage costs, and they want to directly include that into the evo metrics that help determining which algorithm is best.
And for this, maybe let's make first one step back. We want to have good forecasts. Why do we want to have good forecasts? So there's kind of a simple logic, because we believe if we have better forecasts, we can make better demand planning, meaning we have reduced leftovers, or in the food case, we have reduced food waste or stock out, which eventually leads to a cost reduction. So according to this simple logic, we just have to pick the best algorithm, as we've just heard, and then we can optimize our cost. We'll see that it's not that simple, but let's assume from now, let's stick to this simple logic. Now, how do we pick the best algorithm? Ultimately, the goal is to minimize the forecasting error. So if x of t is the actual demand and f of t is the forecast, we want to minimize this error. By the way, for now, we assume that both x and f are available. In practice, this is a non-trivial assumption. Now, we do not just want to evaluate for one point in time, but over a whole period. How do we do that? That's what we're going to discuss during the next couple of slides. I would like to first review some standard accuracy measures or error metrics, and then we'll see that in some cases they're not good enough to make a decision. So we will go to what we call advanced cost-based error metrics, and eventually we even end up with stock-keeping models. But let me start with a short overview, and I think this is the first formula I've seen in the talks today, at least in the talks I was. I'm not sure. So, for those who are fans of formulas, you can be lucky. There are going to be more of them. I think it's probably well known to many of you, at least to those who have worked with forecasts. We have one class of metrics or forecast accuracy measures, the so-called scale-dependent metrics, and the most popular one is the mean absolute error, where we just average the absolute values of the errors over our evaluation period. Similarly, we have the root mean square error, where we take the square here, so in order to ensure that we only have positive values, and then in the end, to keep the scale, we have to take the square root. Now the problem here is, widely used, but the problem is you cannot make comparisons across different time series because of the scale, so that's why people came up with percentage error metrics. For instance, the mean absolute percentage error may be where we just compare our error to the actual demand in this case. And then again, we average over the whole period. Alternatively, we have the class of relative error metrics, where we compare the error to the error of a benchmark forecasting method, and typically people take the naive forecast. The naive forecast just takes the last value as the forecast. So this is the actual demand, and this would be the forecast from the naive forecast, and so this is the error of the naive forecasting method, and we compare our error to this naive error. Now the problem with this kind of metrics is that if you have zeros here in the denominator, you cannot apply it, so it's not applicable anymore, and this happens quite often, especially for like sparse data. That's why people came also up with a fourth class of metrics, the scale-free error metrics, for instance, the mean absolute scale error, where they basically try to average here in the denominator so that we get rid of the problem of zeros. Okay, these are just some examples. Generally, all these metrics have advantages and disadvantages. For instance, the scale-dependent metrics they are pretty simple, easy to understand, but as I mentioned, they do not allow for comparisons across different time series. You can do that with the percentage error metrics or relative error metrics, but you have problems with these zeros. And here for the scale-free error metrics, they kind of fix this problem, but still the question is here, how to interpret the results. What is the economic significance of the results? For instance, if you get out a result for one algorithm, the error is 1%, and for the other one, it's 1.1%. What does it mean? Is it actually relevant? Can we say, yeah, this one is clearly better? Or can we say, or in the end, doesn't matter which one to take? So this is something that holds generally for all the classical error metrics. It's hard to interpret the results. Now you may argue, why should we care? We just take the better one. So 1% is better than 1.1, so we just take the better one. And as long as all the matrices they give us the same results, we don't have to care. Unfortunately, it matters which metric you take. I will show you this with this real-world example. So what you see here is a sales sequence or a demand sequence for a convenience food product. It's the blue line. You see again this typical peaks due to promotions probably. And then we have two models here. A baseline model, or what we call baseline model, this is the red line, hard to see. It basically follows more or less closely the baseline. And then we also have a peak model. The baseline model is not able to predict the peaks, but the peak model is able to predict most of the peaks, but it also produces kind of false peaks, phantom peaks here. And what is better? To follow more closely the baseline and to miss the peaks, or to hit the peaks but for the price that you're sometimes completely off? Now if we apply standard metrics, we don't get a clear answer. There's no coherent answer. For instance, the peak model is preferred by MAE and RMSE, so this is the smaller number here. MAPE would prefer the baseline model, and the relative MAE would even prefer the naive model because the number here is larger than 1. Now, what should we do? Actually, we want to choose the best model. But now we have the problem, we don't know which metric to use. So actually, it's even worse than before. We have now two questions. What model to choose? What metric to choose? How can we decide in this situation? Now, we have observed this kind of problem quite often in our data. And first thing we were trying to understand what is behind this. How can we explain the differences? And for this, we introduced toy models. For instance, the one here where we have so we constructed a toy model or a toy example where we have a sales sequence, which is the blue one, with 5 peaks. We have a perfect baseline model, which is completely on the blue line here, but misses the peaks. But besides that, it's perfect. And we have a peak model, which hits the peaks perfectly, but besides it's always a little bit off. Now again, what is better? Miss the peak, hit the peak for a certain price, and again, if we use standard error metrics, there is no clear answer. Again, MAE and MRC, they prefer peak model, MAPE and relative MAE, they prefer the baseline model. It seems that mean average error and RMSE, they seem to put a heavier penalty on single peaks, because for the baseline model, we just have, we are always perfect, but we don't have the peaks. So there seems to be a heavy penalty for that. That's why they favor the peak model over the baseline model. Why is this the case? This is something we will see later. Now, if I summarize the two results from these examples, we can say that we have an incoherent picture with regard to error metrics. And by the way, we can also use other standard error metrics or from the literature. Problem is not remedied by these metrics. Now, how should we resolve the situation? We're actually not really interested in the metric as such. We want to figure out which one is the best algorithm. And the actual core question that is of interest in order to decide that is, what is the economic significance of the forecast? Or in other words, we want to know what are the consequences in terms of costs that come along with the forecasts. And if we would know that, then we could decide which one we should take, which one of the algorithms. So the idea is that we kind of try to incorporate costs in our metrics. Now that's not so easy because, as we have probably felt from Peter's introduction, costs are product specific and market specific, and real costs in the supply chain, they depend on many factors such as the whole stock keeping process, the ordering process, like safety stock, etc. So here we have to make some simplifying assumption, and One is that forecast errors and costs are in a direct relation and do not depend on the history. So the error directly translates into costs, which is, for the food, or example of ultra-fresh products, actually more or less naturally given. If you have fruits or so, then if you order too much or if your forecast is too high, so you have a positive error, then you have to throw away your food, so you have food waste cost. If it's too low, you have to stock out cost. We then defined a generalized class of metrics, which we called mean cost error metrics, where you basically have two functions here, a cost function that translates your error into costs, and then you also have scaling function. And you see the two scale-dependent measures, MAE and RMSE, are just two special cases of this generalized class that assume very specific cost error relationships. So you just have very specific assumption about the cost error relationship. If we want to come closer to real costs, we have to somehow incorporate the costs in the metric. How can we do that in a simple way? The simplest assumption is that we neglect economies of scale and assume proportionality, meaning we have a linear relationship between the error and the cost. This typically leads to this kind of asymmetric cost error function, where you have on the right side a slope A that corresponds to cost per unsold item. So if we have food waste, for instance, then we have a certain cost per unsold item. This results in this A slope, and on the left side you have stock out, so we have the non-realized profit for a stock out situation. Okay, for ultra-fresh products this is more or less naturally given. We really have food waste and stock out costs. In practice, you may argue it's pretty hard to determine A and B exactly. But luckily, we don't need to do that. If we just want to decide between models, we can just live with an estimate and then perform a sensitivity analysis. Actually, we even only have to estimate A over B, so food waste cost compared to stock out cost. And this is, for certain product classes, pretty well known, at least as an estimate. If you have like a product base price for fruits, for instance, and price of sale, then if you have to throw away the product, this would be the food waste cost, and this is the non-realized profit, so this is stock out cost. For fruits or so, this is typically 80% to 20%, so X is about 4 for fruits, as an example. Now, if we want to compare two models, we can do that by introducing this performance ratio using this linear mean cost error, and we can interpret it as a function of this ratio X, food waste cost versus stock out cost. And all we have to do, so this is the longest formula here, we have to decompose this metric into a sum of positive errors and into a sum of negative errors, which is actually straightforward. For our example, we can do it analytically, and we will end up, well, if we compare the baseline model and the peak model, with this simple function here. Now, what kind of insight can we gain from that? Now we can draw this function here, and please draw your attention on this on the intersection of the curve with the straight line at 1. This defines a critical point. On the left side, the function is larger than 1, so meaning the peak model performs better. On the right side, we have the baseline model that performs better. In other words, if we interpret it in terms of costs, the peak model performs better if the food waste cost per item is about smaller than about 2 times the stock out cost. Remember the baseline model, it's perfect, but it just misses the peaks. So there you have heavy stock out situations. And if you have high stock out costs compared to food waste costs, then you're here on the left side, then the baseline model is not a good choice. That's why the peak model would be preferred. And MAE, for instance, assumes that stock out costs and food waste costs are equal. That's why it prefers the peak model here. We can do the same kind of analysis for our real-world example, and we can also compare more than just two models against each other by just defining a benchmark model. For instance, again, we take the naive model as a benchmark, and then we get plots like this, now here for 3 models. So this is the benchmark model, the naive model. Blue one is the peak model that hits the peaks but is sometimes off. Otherwise, green again is the baseline model. And now we have 3 regions. In this region here, if the food waste costs or if the stock out costs are larger than the food waste costs, we should prefer the peak model over the baseline model and then the naive model. Then here in between, the baseline model is better than the peak model and better than the naive model. And here in the end, the naive model even becomes better than the peak model. So in this way, we can kind of judge in which region we should look for the performance of our models. Let me quickly recapitulate what I've talked about here. We started with the assumption that costs and errors are in a direct linear relation, and there's no dependence of the costs on the history, and that we can estimate economic consequences by estimating the 2 parameters, cost per unsold item and non-realized profit per item for a stock out situation. And then finally we can perform a kind of sensitivity analysis to assess the advantages of different forecasting models, and we also get kind of a judgment or a statement about the economic significance of the results.
We also validated this development of these cost-dependent error metrics in so-called stock keeping models. Now I won't go into too much detail here. The idea is you can actually simulate a logistical process by thinking about what stock at the end of the week T is and what you have to order for week T+1. Now you can do that very simple, but you can also do that more complex and include some service level, meaning that in 99% of the cases you want to be able to meet the demand. You can incorporate shelf life into such models, and you can incorporate transport logistics. So we did that for this real world example, with the supply chain features of a pasta product. So we have 10% stock keeping costs and a 20% margin at the service level of 99%. And we see here very well that the baseline model that doesn't capture the peaks produces a lot of opportunity costs, whereas the peak model is very efficient here. So the total costs, being stock keeping and opportunity costs, are clearly in favor of the peak model. Now with this ratio here, or with these numbers, we can determine A and B from these cost error metrics from before. And if we make the comparison to what Thomas has explained us, it's no wonder, because the ratio is approximately here 0.5, right? 10% divided by 20%. So we are definitely here in the regime where the peak model is clearly favored. All right. Now we've been only focusing in this talk on this very green line here. Of course, we could fill another hour by just talking about forecasting methodologies and how we would incorporate human expertise and so on. So that's all, of course, very exciting, but we thought that actually this thing can also be quite revealing. It has advantages and disadvantages. One of the big advantages is that you can really evaluate your forecast in terms of costs. Your disadvantages are, of course, that it may be very process dependent.
So, and to conclude our talk, all you know the famous quote that all models are wrong, but some are useful. Don't forget about the error metrics. The same holds for the error metrics. All error metrics are wrong, but some are useful, and I hope we could present some useful ones to you today, and thank you very much for your attention.
Thank you.